So this is chapter 15, chemical equilibrium. So we will talk about the concept of equilibrium, equilibrium constant, expression, how to use expression to solve problems, and factors that affect chemical equilibrium. So what is the concept of equilibrium? So when we look at this equation given to us, N2O4 forms 2NO2, and you can see the double-headed arrow here. First of all, double-headed arrow indicate that this reaction is at equilibrium. So when we see the reaction, we would say that the reaction reached equilibrium. From chapter 14, we know how to write the rate of the forward reaction. So imagine this reaction is elementary reaction. And the rate of the forward reaction from left to right will be equal to the constant and the concentration of the product raised to the power of its coefficient. And the rate of the reverse reaction will be the constant and the concentration of NO2 raised to the power of its coefficient. So this just shows to us that the concentration, so this is N2O4 is the reactant, and the concentration of the reactant over the time, of course, has to decrease. It has to be consumed. And the concentration of the product being zero at the beginning, it starts to increase because now we are producing this product. So the time passes, and at some point, this is a point where those concentration of those two substances, the reactant and the product, they are the same. And after that time, their concentration are not changing anymore. So this is the concept of the equilibrium. The concept of equilibrium means that what is equal here, first of all, rate of the forward reaction equal to the rate of the reverse reaction. And another important thing is after that point, we do not see the changes that happen to the concentration of either reactant or product. So this is this graph, the concentration versus time. The second graph shows us the rate of the forward and the reverse reaction versus time. So first we can see the forward reaction has a highest rate. At that time zero, the reverse reaction is really didn't start yet. As the reaction, the time passes, the rate of the forward reaction will decrease, of course, because the reactants are consumed. There is less collision between the reactant particles, and the rate of the reaction should decrease. But the rate of the reverse reaction starts to increase because the products are forming, the more products are formed, products were able to collide with each other. And at some point, this is the point in time when those two rates will be equal to each other. The forward and the reverse reaction, they will have equal rate. This is we call equilibrium. When the rate of the forward reaction equals to the rate of the reverse reaction, this is the equilibrium. So this is the important things we have to remember about the equilibrium. First of all, equilibrium is a dynamic state. Dynamic state means that when the equilibrium is established, you still have both reactions happening. Forward and the reverse reaction will continue to happen. But what is happening, there is normal products form and normal reactants are consumed. Are not, as the reactants are consumed to make products, products will form reactants back. So this is the important thing, is that the reaction will not stop occurring. It will be a dynamic state. But the only thing is the rates are equal to each other, and we will see no changes in the concentration of the reactants and products. At equilibrium, the rates of forward and the reverse reactions are equal. And another thing is the equilibrium can happen when we only have reactants, no products. You can have only products, by the way, and the products will go and form reactants. Or we can have a mixture of the reactant and product in the reactant vessel. For that reaction, the reaction will reach the equilibrium, and the forward and the reverse reaction will have the same rate. So how can we calculate equilibrium constant, and what does the magnitude of the equilibrium constant really means? So this is the equilibrium, but the rate of the forward reaction equals to the rate of the reverse reaction. For the equation that we have before, this is the expression for the rate of the forward reaction. It will be equal to the rate of the reverse reaction. And if we have the ratio between those, so if we divide them, of the forward reaction over the constant of the reverse reaction, we will see this is the expression, the concentration of NO2 at equilibrium. This means equilibrium concentration raised to the power of 2, because the coefficient of NO2 in the balance equation is 2, versus the concentration of the reactant at equilibrium, and the coefficient is 1 and the power is 1. So this is the expression for the equilibrium constant. This is equilibrium constant. K is a constant. C means we are calculating the constant using concentration. That C means concentration. So this is the equilibrium expression. In equilibrium expression, you have to look at the balance equation. Products, you have to put in a numerator. Reactants will go into the denominator. So this is the reaction. So Kc, C means concentration were measured. The product will go to the numerator. It will be raised to the power of its coefficient. The reactant concentration will go to the denominator, and the power is 1 because the coefficient is 1. So there is another important variable we need to know. It's a QC. That's a QC. It's a reaction quotient. A reaction quotient is a fraction. When product concentration we write in the numerator, reactant concentration we'll write in the denominator, and each concentration is raised to a power equal to their stoichiometric coefficient in the balance equation. So if I have this general equation, A plus B makes C and D, once again it's a double-headed arrow, tells us that we have equilibrium. QC, it's a reaction quotient, it's a fraction. It equals to this expression. Do you see there is no EQ over here? Because those concentrations are not the concentration at equilibrium. This is just the concentration at any time, but not necessarily they're not at equilibrium. But if QC will be equal to Kc, and the concentration at equilibrium, and our reaction already reached the equilibrium. This expression is known as the law of mass action. So this example is given to you in ALEKS. When you will read textbook, you will see this sample problem 15.1. They're giving you reaction. They're giving you the equilibrium concentration of all of those species, and they're asking you first write the equilibrium expression, and then determine the equilibrium constant for this reaction at 74 degrees Celsius. So we will write the equilibrium expression. We will look at the balance equation. It will be concentration of the product raised to the power of its coefficient over the concentration of the reactant, also raised to their power of 1. So as you see, this is the product. The reactants, we multiply the concentration of those reactants. We do not add them together. We just multiply the concentration of the one reactant to the concentration of another reactant. And then we will substitute with the number to calculate the Kc. So this is the QC. So the QC, we calculate the value for the system which is not at equilibrium at any point during the reaction. It is very important to know the QC, because once you know the QC and Kc, we can see how far away the reaction is at equilibrium, which we will talk about that later. So once again, we can look at the graph, and also we can calculate the QC at any point. At any point, we have the concentration of the reactants and the concentration of the product, and we can calculate the QC. So again, this is the sample problem 15.2, which is also given to you in the textbook, which is on the ALEKS website, and you can look at that, and the solutions are given to you with the explanations. One of the things the equilibrium constant tell us, as I was telling you, the extent to which a reaction proceeds at a particular temperature. So you can look at the value of the equilibrium constant, and there are three outcomes that you can say. You can say if the reaction will go essentially to completion at equilibrium, the mixture will only consist predominantly of the product. This is really a goal of any chemist if they will conduct any experiments, any chemical reaction. This is what they wanted to have. They really wanted to have a reaction that should go to completion and have products in equilibrium mixture. Another outcome is that the reaction will not occur to any significant degrees, and what we will have in our reaction vessel really just the reactant. So the reaction really is not that successful. And the third outcome is when the reaction really have a mixture of, the mixture has the very large amount of both reactants and the products when the equilibrium will be established. So really did not go to a significant degree to completion. So you have a lot of reactants, but you have a comparable amount of the product also formed. So when the magnitude of Kc is very large, then we will see the first outcome, meaning that we will have a lot of product when the equilibrium will be established. So do you see when this reaction, for this reaction Kc is 10 to the 7th power, that means when the equilibrium will be established, that means this reaction in the vessel will have a lot of product, and not that many of the reactant is still left there. So when the magnitude of the Kc is very small, take a look at the Kc for this reaction, 10 to the negative 25th power, then we will see that the reaction really did not form any significant amount of the product. We have a lot of reactant, nitrogen and oxygen gas present, and the reaction did not make any significant amount of product, as I said. An equilibrium constant that falls between those numbers, 10 to the second power and 10 to the minus second power, it indicates that neither product or reactants are strongly favored. So it's a mixture of both reactant and the products present in the vessel at equilibrium.